There is a lot of material we're covering today. But what I will tell you is the first part of the lesson, about the first 10, 15 minutes, is guaranteed 2, 3, 4 questions on your diploma exam asking this stuff. Like I can predict it with 80% of accuracy. 80% of the time you'll see 4 questions related to this stuff. There are 2 things we need to talk about to begin with here, and we're talking now not about a single object and its momentum. Listen, we're not talking about the tennis ball. We're going to be talking about the tennis ball and the racket together. We're talking about the 2 objects. We have said that if you want to change the momentum of an object, you need to apply a net force. Well, if I want to change the momentum of a tennis ball, it has to make contact with something else to apply the force to the tennis ball. So we're talking here about interactions between objects, and this means collisions. Collisions can be classified as elastic or inelastic, and take any preconceived notion you have of what the word elastic means and throw it out the window. Doesn't mean necessarily what you think it means in physics. On the other hand, the environment in which collisions occur, not the collision itself, but the environment in which it occurs, can be classified as being isolated or non-isolated. If it is isolated, we'll be able to apply the law of conservation of momentum to the collision. If it's, on the other hand, in terms of the collision itself, if it's inelastic, we'll be able to calculate the energy lost. There's an awful lot swimming around here in this lesson. So I'm going to start off with some definitions, and we will explain them. An elastic collision is a collision in which kinetic energy is conserved 100%, which is so rare in nature. So when you have 2 objects collide, they might each have kinetic energy to begin with, and then they might each have kinetic energy afterwards. If you calculate the kinetic energy of the one object and write it down, and you calculate the kinetic energy of the other object and write it down before, and you add them, and then you calculate their kinetic energies afterwards and add them, if you get the exact same amount, it's elastic. Can anybody tell me why elastic collisions out here in the macroscopic world are very rare? We start off with a different question. If kinetic energy is lost, where do you think it goes? Does it disappear from the universe? Charlie?
It's usually lost in waste or like thermal energy.
Thermal energy is the perfect answer. If kinetic energy is lost in a collision, there is thermal energy, also known as heat. Things get hot. If you've ever done any construction work and you're hammering nails repeatedly, next time you do that, feel the head of the hammer afterwards. It's warm. Okay? If you start clapping your hands, and already I can feel the warmth and the tingling in my hands, you're getting heat. And the reason is, what heat is a random motion of molecules. So when you have a collision, the molecules move faster. If I were to take a rubber ball, and bounce it, I mean, we know, I'll bounce it towards the camera so Anna can see this, but we know that it's going to bounce, but it's not going to bounce as high each time. That means it's not rebounding off the floor as fast. If it's not rebounding off the floor as fast, it's losing kinetic energy. And believe it or not, every time that ball hits the floor, that little patch on the floor, the molecules that compose that patch start moving faster. And the molecules in the ball start moving faster. So the ball heats up, the floor heats up. Eventually it's all lost to heat. Even, and this is the classic demonstration that we do, do you have a formula sheet? We're going to go here because that way the camera can see it. Hold up your formula sheet for me, please. And hold it up so that it's angled. Turn it 90 degrees that way, yeah. Hold it up like that. So I've got 2, I don't know what they're made of, steel spheres. Smell that. It's actually, you know, I've created an addict. You can smell that it's burnt, can't you? And you can actually see it burned a hole through the paper. Just that action of hitting these 2 things together. And it doesn't produce a spark. It just burns a hole. There's that much heat. If you look carefully at it, it almost melts the paper. Like the paper gets this kind of sheen to it. So during a collision, if kinetic energy is conserved, which means there is no thermal energy produced, we call that elastic. And in the macroscopic world, pretty much anytime you have a collision, there's heat. Even, taking an aluminum bat and hitting a ball, that spot on the aluminum bat will be a little bit warmer and the ball will be a little bit warmer. On the other hand, an inelastic, so the total kinetic energy before is equal to the total after. An inelastic collision is what we most often observe. An inelastic collision is one in which you do lose kinetic energy. Okay, so if kinetic energy is 100% conserved, and you can put your formula sheet down now, if kinetic energy is 100% conserved, it's elastic. If you lose kinetic energy, it's inelastic. And this is the first kind of definition you need to know. I should be able to give you on an exam or in a lab situation information about the initial and final speeds of two objects in a collision with their masses, and you should be able to determine if it's elastic or not. Okay? Just one final note here. As Charlie said, the loss of kinetic energy, if kinetic energy is lost, is mostly due to thermal energy. There is some sound energy, but it pales in comparison to how much thermal energy there is. Now we're on to something different. Again, as I like to say, when I start to talk about type of collision, elastic and inelastic, compared to type of system, which is the environment in which the collision occurs, systems and collisions are as different as the taste of a cheeseburger and the color of my eyes. There's no connection between them at all. There's a little bit of a connection, but they're different things. So what is an isolated system? An isolated system is a system that includes two objects that are acting on each other, and the net force, the total net force is zero. How is that possible? Well, it's very simple. When that tennis racket hits the tennis ball that we were talking about earlier, the tennis ball, I'll do my best here. Tennis racket. Just go with it. I don't know how to draw a fuzzy tennis ball. Tennis ball. If the racket moves against the tennis ball in this direction, the racket is moving, let's do this. The racket is moving to the right, and it hits the tennis ball. Then the fact of the matter is, there will be a force applied, a net force applied to the ball. But the ball will exert a net force on the tennis racket. This is really Newton's third law of motion. If I go over to you and I shove you, I get shoved back a little bit. Would never do that, but you get my idea. If I put my keys on a desk and I do a one-handed arm stand on them and I push down on the keys will push up on my hand, leaving an imprint. Whenever two objects push off of each other, object A exerts a force in one direction that is exactly equal but opposite to the force that object B exerts on object A. Are you with me on that? So you might ask yourself, if there's a collision between two objects, how could it be otherwise? How is it that the net force is not zero? So you have two objects colliding, and yet I'm telling you the total net force is not zero. And maybe, you know what, I should go back just a second here. I hope you understand that these two net forces are each not zero, but when I add them together, I get zero. That's what I mean by total net force. Okay. How could it be otherwise? How could I have two objects pushing off of each other and Newton's third law is somehow violated? The answer is really simple. During the collision, there's another force that you're just not aware of, or it's not accounted for. Maybe during the collision, there is a very large outside force of friction that you're not taking into account, and that force of friction is acting on one of the objects but not the other. I'm not talking about the friction between the objects, I'm talking about the friction on the objects from elsewhere. So if it's a non-isolated system, there are forces that you're not aware of, or you're not talking about, or they are unaccounted for. I don't like this, but on a diploma exam, they will usually almost always equate these other forces with friction. And there's a problem with that. I don't want to walk down that road right now. But usually you see, during the collision, there are no outside forces of friction. Oh, okay. No outside forces of friction, isolated system. During the collision, there is a significant outside force of friction, non-isolated. This is very important because, and I want to walk through this, and then you might not follow every little detail, but we'll come to a conclusion that is invaluable. The impulse experienced by each of the two objects in an isolated system during a collision, the impulses have to be equal but opposite. And the reason goes back to, I won't use a tennis racket, let's just use two objects colliding. The blue sphere moving to the right, colliding with the green sphere moving to the left. So they are going to be moving in these directions. Well, I don't want to get into that yet. They hit each other and bounce away. What this means is that there is a force on the blue sphere in that direction. This is the net force on the blue sphere due to the green sphere. There is an equal but opposite force that's a net force acting on the green sphere due to the blue sphere. Those two forces are equal but opposite. So it's isolated because the total net force is zero. And listen to this logic. The time that the force is being applied to the blue sphere has to be the same amount of time that the force is being applied to the green sphere. And the reason is they are forcing each other only when they're touching each other. So their two forces start the instant they touch, and those two forces end the instant they separate. So these two forces, is this a correct statement? I'm going to be really picky here. Craig, are these two forces equal? I get the feeling you sense it's a trick question. Yeah. It is a trick question. Are these two forces equal? How many of you say they are equal? How many of you say they are not equal? So we have a whole group of people that don't want to say anything. Why are they not equal, Fazile? Because they're in opposite direction. Force is a vector. Direction is important. These are equal but opposite. So if I were to calculate F delta t here and F delta t here, I'd get the same number, but one of them would be positive and one of them would be negative. So this is why the impulse experienced by each of the masses are equal in magnitude, but opposite in direction. This leads to that statement. And I'm going to explain this once and maybe again later, but the explanation I think is interesting to hear, but it's not crucial. Why does the momentum have to be conserved? Because impulses change in momentum. So if I'm telling you the impulse experienced by one object is a positive amount, and the impulse experienced by another object is a negative amount, that means one gains a certain amount of momentum and the other loses a certain amount of momentum, which means the total momentum in the system stays the same. So, in an isolated system, if a collision occurs in an isolated system, momentum is conserved. That's an awful lot to absorb so far. Elastic collisions are one in which kinetic energy is conserved. Inelastic collisions are ones in which kinetic energy is not conserved. If a collision occurs in an isolated system, momentum is conserved. And if it doesn't occur in an isolated system, momentum is not conserved. This is an opportunity, one of the rare ones in this course, for you to actually study this stuff. Memorize it. You need to know all of that. So momentum is not conserved here. The law of conservation of momentum says that in an isolated system, the total momentum before and the total momentum after are equal. I mean, you understand this from earlier grades, right? If you say mass is conserved, you say the total amount of mass before is equal to the total amount of mass after. This is the meaning of a conservation law. This is an interesting point. Momentum can be conserved in elastic collisions and in inelastic collisions, because it's not the collision, the type of collision, that determines whether this is true. It's the system in which it occurs. So that's a little bit tricky. Whenever we use this, we have to include direction. And today we are talking, if you were to look at the title of this, we are talking about linear momentum. We are limiting ourselves today to collisions between objects where the objects move to the left and right, or up and down, or north and south, or east and west, but not in all kinds of wacky directions like the pool balls on a pool table. That's for Friday and Monday. We will look at those collisions later. What this means, everybody, is if you have an object moving to the right, you should assign its velocity a positive. Don't get ahead of me, please. If you have an object moving to the right, its velocity should be assigned as positive, and to the left should be negative, or whatever you decide. Look, I've had students in the past that go, I'm going to use positive as left, just to be clever. Hey, if you want to do it that way, that's fine. Just don't get confused.